My presentation and paper is called Unlabelled Necklaces in Lexicographical Order and Grey Code Order, which sounds a little bit complicated, but I'm going to explain it now. So my paper was about was investigating how to list all K-Eri length N unlabeled necklaces efficiently. So a necklace is a subset of strings that contains all strings that can be obtained by rotating one string, while an unlabeled necklace is the same thing, but you can also use relabeling. We consider two orders for the listing: the lexicographical order, which is essentially the ascending order, so smallest to largest if we treat the strings as numbers for when k is less than 10, and a grey code order, where the strings appear in a generalized variant of the binary reflected grey code, also shortened as BRJC for K-Eri strings. There is already efficient algorithms that can generate binary unlabeled necklaces in lexicographical and BRGC order, and there's also an example for K-Eri necklaces, but not unlabeled, which is what mine is about. As part of my experiments and paper, I wanted to check if the trends observed in the previous studies can also be used for k equals 3. Specifically, in the first computer experiment, I calculated the average length of the suffix that forms the difference between two consecutive ternary, so k equals 3, unlabeled necklaces in lexicographical order. If the trend follows on from binary, we would expect that the average suffix length will not grow with n, and my result did confirm that that was indeed the case. The second experiment, we listed all ternary unlabeled necklaces in grey code order, and I calculated the maximum number of different characters between two consecutive strings. If the trend had continued on from binary, we would expect the maximum difference to be 3. However, this was disproved by the experiment, as the observed maximum difference was 4. We can then conjecture that the maximum difference is k plus 1 for K-Eri unlabeled necklaces. So the background for my thing, because that whole instruction might have sounded a bit complicated and not really explained what a lot of things are. So if you're familiar with binary strings, this is like a generalization of this. So a K-Eri n string is a string of length n, which consists of numbers from 0, 1 through to k minus 1. For example, a binary string of length 4, e.g. 1001, would have n4 and k equals 2. And then there's also another example beneath that for k equals 3, so it's got 0, 1, 2. And then you keep going on. Lexicographical order, as I touched on previously, for this example is essentially just ascending order, but it's a way that we order sets of information, and you can see it also in the dictionary with it being in alphabetical order. The formal definition of this, because since all strings in our settings have the same length, a string A precedes another string B in the order. If the first index I, where two strings differ, the letter of A is smaller than that of B, that is, the index of A is smaller than the index of B. For k, as I previously mentioned, if we consider the strings as numbers, we just list them from small to largest, so it's not really the formal definition isn't really needed here. So for example, as you can see, they're just listed in smallest to largest. And then this is about unlabeled necklaces. A necklace is a subset of strings that contains all strings that can be given by rotating one of the strings in the set. So you're moving the last one to the first position, and you keep going around till you gain all of them. You can see a picture on the left describing, showing what that would look like visually. To represent a necklace, we use the lexicographically smallest string, which in the case that I've mentioned above. So if we had the necklace of 0221, 1022, 2102, and 2210, it would be represented by 0221, because as you can see, it's the smallest number. An unlabeled necklace is a set of strings where each string can be obtained by rotating and or relabeling another string in the set. Relabeling is where we swap the numbers of the original string to another number within the range to obtain a new string. So, for example, 1201 could be relabeled to 0120 because all the ones get relabeled to zeros, all the twos to ones, and all the zeros to twos. For example, 2001, 0221, and 1102 belong to the same unlabeled necklace. This is because 2001 can be relabeled to 0221, and 0221 can be relabeled to 2110, and then rotated once to the left to create 1102. The combination of the nexus 0012, 0021, 0112, 0221, 0122, and 0211, each represented by the lexicographically smallest string, as I previously mentioned, forms a single unlabeled necklace, which is also represented by its lexicographically smallest string 0012. The binary reflected gray code, also shortened to BRGC, is a listing of binary strings where each consecutive binary string changes by 1 bit. This is the BRGC for n equals 3, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. The way that I like to think of it is if you've ever done any like word ladders, which is like a puzzle thing, it's kind of similar to that. So there's multiple ways to generate them. One way is to flip like like each bit of the string, so 0 goes to 1 or 1 to 0, to the rightmost bit in order to obtain an unvisited string. For example, 000's rightmost bit is flipped to create 001. Then we flip the second rightmost bit, which in this example is the middle bit, as flipping the rightmost bit would generate an already visited string. 0, 0, 0 to obtain 0's 1, 1. Then we flip the rightmost bit again to create 0, 1, 0. And then this process continues until we've generated all the strings in BRGC order. For unlabeled nexuses in BRGC order, if we take the BRGC and remove the strings that are not necklaces, then we obtain a list of strings where consecutive nexuses differ by at most 2 bits. Removing the strings that are not unlabeled nexuses yields a list where consecutive strings differ by at most 3 bits. Generating binary unlabeled nexuses in lexicographical order with suffixes. There's an algorithm from a previous paper that generates all binary unlabeled nexuses in lexicographical order, which runs in constant amortized time. This means on average, the time taken to generate the next string is constant, which means its time complexity does not depend on n, which, if you're familiar with any kind of programming and time complexity, is a very good thing. Essentially, the algorithm removes a suffix of the current string and then adds a suffix of the same length to obtain a new string. A suffix in this context is a block of any length of continuous characters at the end of a string, e.g. the non-empty suffix of A, B, C, D, E are E, D, E, C, D, E, B, C, D, E, and A, B, C, D, E. The runtime of the algorithm suggests that the average length of the suffix that is added to generate a new string is bounded by a constant. For example, a list of binary unlabeled nexuses of length 7, k equals 2, n equals 7 in lexicographical order, with the length of the suffix added / removed is shown on the right. As you can see, the number doesn't change very much in the, if you look at the little box, it doesn't change very much. So the maximum's 4, but it's, the maximum's 5, sorry. But it doesn't, there isn't a big range of numbers. The average is 25 out of 9 if we take all of those values and then calculate an average. So if the average does not greatly vary between different values of n, we can see that this suffix approach can potentially yield constant amortized time, which is what this paper uses. And I wanted to see if it worked for different values of k. Generalized BRGC is a gray code for k-area strings, not just binary strings. That means the string is ordered in the same way, where each consecutive string only differs by 1 letter. In the investigation, we use the generalized BRGC, which we'll simply refer to as gray code from now on, where the next string is obtained from the current string by adding one or subtracting 1 from an entry. For example, the list for n equals 2 and k equals 3 is as follows, as you can see on the presentation. So on to my methods. So for the first experiment, so I listed all unlabeled nexuses in lexicographical order. So my algorithm needed to list all unlabeled nexuses. It needed to take n and k as an input and then output all unlabeled nexuses of n length using characters in the range 0, 1 to k minus 1. First, we generate all strings of length n using the previously mentioned range, then remove all the strings that are not a representative of an unlabeled necklace, and then finally, I would then output the final list of unlabeled nexuses. So to do this, first I created a Python program that allows us to input k and n. Then I created a list, which would be the range of characters that I'm able to use, and then I use that list to generate all k array length n strings by using the product tool from itertools. After that, I created a function that could rotate strings using string manipulation and a function that could relabel strings using permutations from itertools. Using these two functions, I went through each available string and relabeled and or rotated each one and then kept the smaller string. So that would be the lexicographically smaller representation. So the large string would then be appended to the list to remove. After going through all the strings, I removed all the items in the to remove to only leave the unlabeled nexuses. I didn't actually have to manually put them in lexicographical order, as it generates them already in lexicographical order or ascending order. Well, actually, you can't see the code in the appendix, but that's in my research paper. And then for calculating the average length of the suffix that forms the difference between two consecutive unlabeled necklaces when in lexicographical order for different values of n for when k equals 3. As I mentioned earlier, it is implied from the previous mentioned paper that the average length of the suffix that forms the difference between two consecutive binary unlabeled necklaces when in lexicographical order will not grow with n, as that is the condition that allows the algorithm to run in constant amortized time. In order to verify if this also holds true for k equals 3, after outputting the list of ternary unlabeled nexuses by using the algorithm in the previous subsection, I calculated the average length of the suffix that forms the difference between two consecutive unlabeled nexuses by working out the length of each suffix and then working out the average suffix length. For my next experiment, there was listing all unlabeled nexuses in grey code order where k equals 3 and calculating the maximum difference between two consecutive strings. So the algorithm needed to generate and output the grey code order for k equals 3, and it needed to input n, generate the grey code, remove all strings that are not unlabeled nexuses, and then output the unlabeled nexuses in that grey code order. So to generate the grey code, I adapted some code that generates the BRGC for k equals 2, because obviously it's binary. The function uses recursion to generate a list of the grey code, with the base case being n equals 0, so the current list is currently empty. Then it adds 0 and 2 to the front of the current strings in the list and 1 to the end of the strings in a reverse version of the list. These new strings are then added to the list with the old strings replaced in the process. After that, these newly generated strings are added to the list, which would now look like 0, 1, 2. This continues again to create another list, the new list, which would be 0, 0, 0, 1, 0, 2, 1, 2, 1, 1, 1, 0, 2, 0, 2, 1, 2, 2. This function keeps on going until the strings are of length n, so then we have the grey code. Finally, I kept only the unlabeled nexuses in the list and output the result, then calculate the maximum number of different letters between two consecutive strings by calculating the number of different letters between each pair, and then choosing the maximum value. So here are my results. So for the first experiment, it was calculating the average length of the suffix that forms the difference between two consecutive unlabeled nexuses when in lexicographical order for different values of n when k equals 3. Sorry. So this comes from the previous paper that ran in constant amortized time. So as you can see on the left, there's a graph showing the results of my experiment. As expected, the average suffix lengths have not really grown with n, because you can see that it plateaus once it reaches n equals 5. And there isn't that big of a range, it's just because the scale is quite small. This shows that it is possible to have an algorithm with constant amortized runtime when using the suffix technique, as the change in suffix is not largely affected by n. So it does work for k equals 3. For the second experiment, which would be listing all unlabeled nexuses in grey code order where k equals 3 and calculating the maximum difference between two consecutive strings. On the left, you can see the graph again. Remove the graphic results again. Removing all strings but the unlabeled nexuses for this data set has a maximum of 4. This didn't fit within the expected trend of a maximum of 3, which likely comes from the changes between ternary and binary. We only have the results for a small amount of values of n, and it could be that the difference will suddenly increase, e.g. n equals 10. However, it could still be the case that this maximum is upper bounded by a constant, which is in this case 4. We can conjecture that generally the maximum number of different characters in two consecutive k-ary unlabeled nexuses in grey code order is k plus 1. If you wanted to test this, we could conduct an experiment for k equals 4 and see if this still holds true, the maximum being 4. If this holds true, this approach becomes less effective at generating unlabeled nexuses officially as k grows, as it will take longer to change strings to another. So as I mentioned earlier, it wouldn't be based on a constant, it would be based on a natural variable, so obviously it would grow and then become more. So to conclude, I investigated how to list all k-ary n-length unlabeled nexuses in both lexicographical and grey code order. As shown by my data and graphs, one of the results fit the predicted trends and expectations that were laid out by previous studies, but with ternary nexuses rather than binary necklaces. while the other experiment proved the hypothesis only worked for binary necklaces, so we couldn't use that approach for any other values of K. Future work could incorporate the suffix approach to K-area unlabeled necklaces. Verify our conjecture in section 4, in this section about the experiment that didn't work for K equals 3, and to develop a grey code algorithm to work out for all values of K, because the one I have at the moment only works for K equals 3. I'd like to thank my mentor, Hung P. Huang, for his support, guidance, and mentorship throughout the process. I'm really grateful to be able to work with somebody who's actually in the industry. He's an actual professor in computer science. I've not really had that opportunity before. I'd also like to thank the Talaria program and its team for allowing me to have this experience, and I've really enjoyed my time. And here are my references.